Okay, recording is started. So the first thing I want to point out is our Canvas homepage I changed this afternoon. So I've been putting together some little icons for branding so everything goes together, and these will probably change. This is just a draft as like a placeholder. So if the looks change, just go with it. Look what it says. So these are hexagon stickers. A lot of the R packages, there's hexagon stickers to go with all the R packages. So you get them at conferences, see they're on my laptop. And you'll see them in a lot of websites that most packages have a hexagon sticker, like that's the shape of the logo for our packages. Just someone did it and it caught on, and most people do it. So this first one is for the class. This first one that says EDUC Psych 6600, I think I'm going to change it so it says Statistical Foundation on it instead. This one goes to the website where I have linked all the links to, will eventually link all the links to the slideshows. I'm going to also add another column to this, so we'll have a link to the videos on YouTube. But right now it just has through chapter 5 of the chapter links. There's also a link to the syllabus and kind of an overview of the class up here. This resides on part of my website, my personal website, sarahschwartzstats.com. So that's the first little hexagon. This middle one is new. This one I'm so excited about. Takes us to the YouTube channel that I just put, it doesn't.
They're both together.
They're both together. I'm gonna have to fix that. When I fix that tonight, it will take you to YouTube. And I had put the first video up under my personal name, but I created a stats web YouTube channel. And can I change it? Let's see. I was going to call it Stat Goals, but I didn't like that. It's Sarah Schwartz Stats. Because it's onto Google now instead of YouTube. Okay. Let's see if I can. Okay. I have to change. I've never done YouTube like as a poster. Switch accounts. There we go. So I'm getting used to navigating around in here. So I know how it feels to be in a new zone and like not quite know how to feel your way around. Okay. So I'll fix that link on the website. This is where it'll go to. So this is sarahschwartzstats.com with the R logo on the Superman. All the S's. Statistical Studio, all the S's. So that's what I went with. So right now there's only one class here, and notice I put a little thumbnail so it has those little icons on it. This is the last class we met together. I moved it over here. So today's recording that's being recorded right now will be here too. Tonight or first thing in the morning. I also, just because I thought it might be helpful, on the channels here, I've linked some channels. They were showing up before. Some other statistical channels that you might find helpful. So the videos will all go here for class recordings, and you can watch them from here. So I'll fix that link, and then this link, other one is that they're mushed together, I guess, goes to the encyclopedia, and that has the examples that you can follow along that are just like the homework. Now the encyclopedia will have more examples there that don't match your homework. I'm trying to make it like fully fleshed out for other things. Your homework will, but there should be enough there that match your homework. You should be able to get through the homework. That's the goal. And then here are the optional tools. These are totally optional if you want to throw equations or other fanciness in your R Markdown files to knit. Ignore completely or your heart's content with that, and then the book's still at the bottom of the page. So that's changed a little bit. The next thing I want to do is look at the syllabus, which we are behind on. If you haven't already noticed. Everyone notice that we're behind? So today is the 22nd. According to this, we should be doing chapter 4, but chapter 3, we got to do chapter 3 today. I'm going to try to see how much of 3 and 4 we can both get through tonight. Whatever we don't get through, I'll be making a recording of tonight and first thing in the morning, and I'll send you an announcement when it's up on the YouTube. There'll be the video. So there's a playlist for the in-class recordings, and then there'll be a playlist for out-of-class recordings that I make. And so you can watch those. So next Monday is supposed to be the exam. That's exam day. I was hoping that we would not meet at all during the exam day. But I'm going to be out of town next week, and I'm going to have my RA, Jeremy, come in. And so on the exam day next Monday, he will be here in the classroom to answer questions. He will not be presenting new material. He'll explain whatever. He's great. He can explain anything you need explained or help you with R. He will not code on the test. I will provide output. I will never ask you to write code on the test. That's just me. But you can come here on Monday during class time to get help as much or as little as you want. There will be no attendance. So you could use that time to take the test if you are feeling confident with the material. I am going to be out of email as of Friday night. So I'm going to open this exam. It's not open right now. I'm going to open it, if not tonight, first thing in the morning. So if you want to take it early, if you feel like you got this assignment done, the R part on chapter 4 is like one problem. It's tiny. That should take not very much time at all. So there's a lot of work by hand problems in chapter 4. But if you think you're good here from your undergrad stats and from today and stuff, you can take this exam whenever you want. It's going to close, I believe, Tuesday, right before chapter 5 starts. And Jeremy will be here to lecture for chapter 5 a week from today. Okay? So I'll be out all next week. I won't even get email. I'll be off the grid. So I will put on the Canvas page Tyson Barrett, the other faculty that teaches this class. He has done the Canvas exam thing before. I'll put his contact information so you can get a hold of him if you have any technical difficulties, both him and Jeremy, so you're not just like lost at sea while I'm gone. And the exam you take on Canvas, but the exam should only, hopefully, if I do it right, should take 20 to 30 minutes. Short, more like a quiz. But I will offer it for 2 hours. You can take it anytime between when I get it put up, whether that's tonight or first thing in the morning, until the 28th. So you'll have like a week zone in there. But once you open that exam, you only have 2 hours, and it'll submit at the end of the 2 hours whether you want to or not. It has to be in one sitting. Now, it has to be done with a computer that has a webcam. I guess it has you like show the room. No one else can be in the room with you. You can go in a closet, you can go in a classroom, office, wherever, so you're alone. It is open notes, it's open homework. You can print out your summaries or any of those things that you want. Formula pages. You will be provided with, well, let's make it open book, and then you have your tables in there. You can't use the electronic book though. I will have copies of the tables that you need. I'll always provide formulas and tables that you need. Don't memorize the Z table. Don't. Yeah. So this is not a speed test. This is not a memorization test. It will be very much like the homework, other than you will not be writing code. Okay? Anyone have any questions about timeline and what's expected? Yeah.
We have like our summaries pulled up on our computer. Can we like minimize the test and use our computer? How does that work with that?
So this is my first time using the computer to give the test. So you can take it at your leisure, which I think is great. But I haven't been through the process before. Whenever I've taught this class, I've made it open notes, open homework, closed book, closed computer on pencil and paper. That's how I prefer it. But with the computer, with the way Canvas does an exam, with the using the webcam, you're not supposed to have any other windows open. So I would say if you want to use your summaries, you probably should print them out. Now, you should only print out the chapters that are on this test. So you'll print chapters 1, 2, 3, 4. Yeah, just 1, 2, 3, 4. Those you shouldn't update after this. So those should be stable. And then for the next test, you'd print out chapters 5, 6, 7, 8, 9, 10, and 11. Now at the very, very end, your table of contents will have changed. But those, you should only have to print those once.
So basically we just can't move our screen once it's on.
Yeah, once the test comes up, You cannot leave and come back. You can't open any other windows. You cannot use the calculator on your computer. So you have to have a handheld calculator that is not a cell phone or a tablet or something. Basic add, subtract, multiply, divide calculator. We haven't done anything too crazy yet, have we? In chapter 4, there's add, subtract, multiply, divide, and maybe a square root. A square and a square root is about as crazy as we're going to get in this class. Okay. Doing the standard deviation by hand, that's just like, ugh. I don't even like that. Okay, so there's our schedule. I will be hanging after class again. If you have any questions or concerns, you can always email me. You can always bring it up with me. Okay, so there's class. So let's go, let's see, first, what's due right now? So the summary for chapter 4 is due already, right? So should have read chapter 4 first time through. Yours looks a little different. So summary for chapter 3 is due tonight. I figured out why it was auto-submitting. Do you guys see the announcement? It's when I make a due date and you start it and then I extend the due date. If you've already started it, it submits it at the original due date. But I figured out how to go in kind of and give you more attempts, and it said manually unlock it, but I don't think that worked like I hoped it worked. Hopefully that won't be a problem anymore now that we're not changing due dates. Okay, so homework 3 questions. Let's do the online part and then we can go over our part. Anyone have any online part of chapter 3 questions? Mean, median, and mode. When do you use which?
Use the median when like you're really spread out, like, or extreme.
Extreme or skewness, go with the median. Yeah. If it's symmetrical, you can go with the mean. Mean is preferable if it's symmetric. Median is preferable if we have skewness or outliers. Mode we don't use for calculations very often because the mode just happens to be the value that's the most often. And if we're using very continuous measures, often we have nobody that matches. So that's like not very useful.
I have a question.
Yeah.
There's like a question about a veterinarian and the lifespan of retrievers. If it's
Yeah.
not a whole number, should we round it to a whole number?
You're supposed to do the average?
Yeah, like for the mean, it gives you like a decimal number.
Yes, right here. Here it is. The veterinarian lifespan. Here are the ages. Now these ages are measured in whole numbers, but when you do the math to average them, you will probably get a decimal. Should you round up? That's the question, right?
Yeah.
The answer is no. You should leave the decimal because the mean is the long run average. It is not necessary that it's a actual possible value. So you would leave the decimal. Like if long run, they're going to average between 9 and 10, show that by putting 9 point whatever. To show, is it closer to 9, is it closer to 10, is it right in between? So we use the decimal when we do the calculations that have decimals, we're going to keep the decimals. Now that always brings up the next question, how many decimal places should you keep? Usually if it has lots of decimals, on the homework we're trying to say to 2 decimal places or actually say to 4 decimal places so the computer can grade it. And it usually gives a wiggle room of like plus or minus 0.1 or 0.01 or something like that. Jeremy put those in so that you know, if you round off, then you're still okay. But if you do the calculations on your calculator and it shows 3 numbers after the decimal, use all, and then it stops, use them all. But if it just keeps going off the screen, 3 or 4 decimal places is usually plenty. Don't put down 10 decimal places. We'll try to make sure that the assignments, if you ever see an assignment that doesn't say and you're like, crap, how many do I put? Send me an email. Tell me which, say, you know, chapter 3A, question 4A said to put the average. I didn't know how many decimal places to put. And then we'll get it fixed. Huh?
Well, I went to only 2 decimal places.
2 decimal places?
In chapter 4.
Uh-huh. Does it say?
I don't think it's.
Doesn't say.
Yeah, number 13, question 13 has more than 2 as well, if I remember right.
13?
I rounded it to 2, but I think
2.
it had more.
2 will probably be fine. You never should have to put more than 4. These questions were used last semester by Tyson, but we've chopped them up into chapters instead of like 10 chapters together. Okay. Mean, median, and mode.
The mode is more of like categorical stuff.
Yes.
The frequency.
Yeah. So sometimes if we have like if you're doing a Likert score and the only possible values are 1, 2, 3, 4, strongly disagree, somewhat agree, strongly disagree, the mode would be meaningful there. But if our variable is very continuous, not discrete, then the mode doesn't really offer much in the way of information about the center. All 3 of those are different ways to do the center. There are lots of other ones. Those are the 3 most common. Now, mean is used the most in statistics because it's a calculation, but it is really reliant on that your variables are interval ratio, that it's okay to add, subtract, multiply, and divide. And if you have Likert scales, that might not be the case. So usually that's why we like Likert items to have more than 3 or 4 levels. We want them to have more, but that's not always possible. Okay. Okay, so here's an example of a distribution. How would you describe this distribution? What kind of words?
Positively skewed.
Positively skewed because it's going to the positive number side, not the negative number side. Any other words you could use?
Some outliers.
Yeah, now it really is not so much that there's outliers. Each of these bins up to here are like $5,000. This last bin is $50,000, and then this one's $250,000 and up. So they've done different size bins here because what really happens with income? How far would this plot go? Forever. So there are extreme values, and they've kind of just like squished in the end of the tail to get it to fit on the page. But doing unequal bins like this is problematic when you go to do an average because there's a lot of range. This should be a really wide bin. We don't know where people fall. So doing if you're ever making a questionnaire and you're asking someone how old they are, what's the best way to ask that question? What's one way you could?
Yes. Ranges.
You could do ranges. Are you between 20 and 29, 30 and 39? But if you ask them in ranges, can you do an average? No.
You can ask the exact year.
You could ask them, how many years old are you? Do you think that people are going to be accurate? What do older people, more mature people, tend to do with their age? Crap, how old am I? Am I 40? Am I 42? Am I 41? 40 is close enough. They tend to round off. If you ask people their ages, the distribution is humped at 30, 40, 50, and then another smaller hump at the 35, 25, 45, and because people lose track when you get older. When you're 18, 17, you're really keeping track. When you get in your 40s and 50s, you're like, I don't remember. What might be a better way to get a more accurate indication of someone's age? What year were you born in? 77. I've had that memorized for 42 years. I can give that a lot quicker and more accurate than asking how old I am, because that's changing every year, and I lose track of that. So if we really want to know how old someone is and you want a continuous variable, ask the year that they were born in, and you will get a more accurate continuous variable than doing ranges or even asking whole number ages. There is some ethical concerns, because like with income, are you going to ask someone exactly how many dollars a year they make? What would you do if someone asked you how many dollars a year you make? Do you mean gross? Do you mean net? Is it just me? Is it me and my husband? What if it's a good year? What? It's easier to do boxes. So I'm not saying range boxes are a no-no, but if you make range boxes, no, you cannot treat that variable as continuous, especially if you only have like 4 ranges. Sometimes that's good enough for your purpose, but it's not good enough to treat it as continuous. Okay. So median is better if you have extreme values or skews because it's resistant to change, and the mean is very influenced by an extreme value or skewness. So here are two distributions that are exactly the same, except for this top one has this red value included, this bottom has it excluded. What happens with the mean? Is it the same number? No, it's different. If you have an extreme value, the mean gets pulled towards it. It's like a magnet. It pulls the mean towards the extreme value or the skew tail. If you have the same data sets, the same value removed, what happened to the median? With the value, without the value?
Median is the same.
It's pretty much the same, pretty darn close, if not identical. So the median is resistant to change. It isn't as influenced. So spread, there are at least 3 different ways you can capture spread. The most common we use with mathematical calculations is the standard deviation or the variance. What's the relationship between standard deviation and variance?
Square root.
Square root the variance, you get standard deviation. Square the standard deviation, you get the variance. We're going to talk about range, interquartile range, and semi-interquartile range when we get to the 5-number summary. So what's the best way to summarize your data?
Depends.
It depends. That's my most common answer I give when people ask me questions as a statistician. It depends. And usually there's no perfect model. There's no perfect estimator. There's pros and cons to all of them. But in general, if we have skewed distribution with outliers, we want to go with the median for center and either the interquartile range or the semi-interquartile range for the spread. If we have a symmetrical, no outliers, more normalish unimodal distribution, mean and standard deviation are good. And we're going to rely on that for a lot of our stats. But the best way to know the distribution is to plot it, graph it, histogram, boxplot, something. Okay, skewness. How do you always like that formula?
Yeah.
Yeah. This is the thing you need to know. Skewness measures how asymmetrical it is, how lopsided the distribution is. You can usually detect it pretty good with a histogram or a boxplot visually. Your eyes are actually a lot better than most of the tests. There are tests for detecting skewness, and they use this calculation, but it is oversensitive to big sample sizes and underpowered for small sample sizes. So as a statistician with 20 years in the field, I never base any judgment on that actual number. Generally, we look at the skewness, and if that number, positive or negative, is bigger than 2, we might have some concerns. But that's as heavy as I get into testing it. I never do a p-value test on skewness, even though people do. So we know about positive, negative, 0 is symmetrical. So there's 3 different histograms. The one in the middle, fairly normal. You're never going to have perfectly normal data. The red one is, oh, is it red? It's like pink up there. It's red on this one. Positively skewed, and the blue one's negatively skewed. Okay, kurtosis. There's an even funner formula. Don't memorize that. I'll never ask you to use it. The same basically thing applies, except for these are skewness and kurtosis are always comparing the data to a perfect bell curve. And so skewness is about lopsidedness. Kurtosis is it more peaked or is it flattened out more with more weight or more area, more volume in the tails? And again, usually we see, is it bigger than 2-ish? So here in the middle, that's no problems with kurtosis, a perfect bell curve. This would be positive kurtosis, positive peaks it, negative nukes it. That's how I remember it. Nukes it like collapses in on itself. Okay, so 5-number summary. This is where we're going to hit semi-interquartile range. I have a list of data, not a very big number. Okay, how do I find the min? Smallest number. So it's always helpful to list them from smallest to biggest. I already did that for you. So the min is the smallest, the max is the biggest. What's the median? The middle. So if they're in order, you go farthest out, next in. What happens if you have an even number and you have 2 middle numbers? Which one's the median?
The average.
You average the 2 if there's a tie. Okay. So the median can be a decimal number, just like the mean can be a decimal number. That's okay. So here, if we come in 1, 2, 3, 4 numbers, 1, 2, 3, 4 numbers, there are 2 that tie for the center, so we average them to get the median. To make a box plot, the min and max are the ends of the whisker lines. They used to be called box and whisker plots. We just call them box plots. And the median is the center line. Now what about the other 2 lines? What other 2 values are there for the 5-number summary? Min, max, median's the middle. We don't do mean and mode.
Oh,
First and third quartiles. The lower, sometimes we call them lower quartile, upper quartile, 25th and 75th percentile. How do you find them on a list of numbers? This will be on the test.
You can take
I
median
saw
again.
this 2 weeks ago.
Huh?
You can take the median again of the.
You do the median of the bottom half and then median of the upper half. So if we only, now what about these 2 middle numbers? Do we ignore them or include them?
Include them.
You know what? Some people and programs do it different ways. And I have a whole bunch of articles. If you want to read out more about it, I can send them to you. But generally, they are included, and I will expect you to include them. So the lower half would be these 4 numbers. So what's its median? 79.5. What's the upper quartile? The middle, oh, we got 2 ties, so we got to average those. So what's the upper quartile?
90.5.
90.5. Those values together are called the 5-number summary. On the ends, we've got the minimum, the maximum, median is in the middle, and the quartiles are just the medians of the 2 halves. Those are the 5 lines we draw for a box plot. Now this is a sideways box plot. You can draw it up and down either way. And what do you connect? Where does the box go? The 3 middle, and the whiskers go out. Now in R, the whiskers don't have these little ends on them. They just stop. That's okay. It's acceptable. Now this is a traditional box plot. Most software make what's called a modified box plot. Now if you have, what if I had one value that was 150? A dot. Yeah. We use the software usually puts a dot. This is the rule with software. This is the modified part of a box plot. It only lets the whiskers go out 1.5 times as wide as this box. Now this box is going from the lower to upper quartile. That's called the interquartile range. So what's the interquartile range here? 79.5, 90.5. What do you do with those 2 numbers? You actually have to subtract them. R does not give that to you. R will give you these 5 numbers. You would have to do the subtraction on your own if you wanted the interquartile range. So 90.5 minus 79.5 is 11. So the interquartile range is 11. So it would only let these whiskers be how long? 11 plus half of 11 would be, it only lets them go out 16.5 units. And if there's data past that, it'll make a dot. And some software will, even if it goes 3 times, it'll make a star past that. R doesn't. SAS used to do that. It's just a way to show extremeness. So the interquartile range is 11. What's the semi-interquartile range? What's a semicircle? Half. So if the interquartile range, we subtract our quartiles, is 11, the semi-interquartile range is 5.5. We divide it in half, like you would divide a circle in half for a semicircle. This is a value, this value should be usually close to your standard deviation if it's a symmetrical distribution. If it's a normal distribution. Okay, so box plots, if we have on your homework, there's one you do a box plot for the whole sample or for one subgroup. Usually we don't just make one box plot. Box plots, if we have one set of numbers, a histogram's better. What box plots are great for is comparing subgroups. But I really like these pictures because they show how a box plot can give you much the same information as a histogram. It shows you the range, the center, and the spread. So this top one, this is what a normal distribution will look like in box plot form. Here's the, and is anyone a hiker? you read a map that has like those circles or lines
Same
on
height.
it to show elevation.
Yeah.
You can think of this histogram looking on it from above down. A box plot is kind of showing you some general levels. But see, symmetrical distribution, what do you notice about that box in the middle? Where's the line? The line is dead center. What do you notice about the length of the whiskers? They're symmetrical and they're a little longer than the box. That's what a normal distribution will look like in box plot form. What would you call this distribution? Would the kurtosis be positive or negative?
Positive. Oh, no.
Positive because it's more humped or peaked. If it's flatter is negative kurtosis. So this has positive kurtosis. Now, what do you notice about the shape here? It's symmetrical-ish, but what do we notice about the size of the box compared to the whiskers? The box is wider because the middle half is more spread out. Versus this one is showing, how can we tell it's skewed? Lopsided. What about this one? These extreme values show up as the dots. So this is a plot by R. Now this is comparing treatment to placebo group. You have no idea what this is for, but what can you tell me about treatment versus placebo on the test score? Treatment scored
Better.
higher on average, or in the median at least is higher. If they're symmetrical, the mean and median will be about the same. So it looks like the blue treatment group scored on average higher than the pink control group. What about the spread? Can you say anything about the two group spreads?
Closer together.
Treatment group is a little bit more less spread, and the placebo group is more diverse or spread out. So box plots can help you compare two distribution in center and spread, and that's the benefit of a box plot. A lot of the methods we're going to use, like t-test and ANOVA, have a basic assumption that the two groups we're going to test if the averages are different, assuming the spreads are the same. And how do you know if the spreads are the same? Side-by-side box plot eyeball test is a really good way. There are density plots too. We're not going to get into them too much. We are going to hit a QQ plot in chapter 4. So chapter 4 is about the normal distribution. A QQ plot, sometimes it's called a quantile plot. Some software call it PP plot. I don't know why. It seems weird. It's a little bit complicated to make them. I made one by hand once and it was no fun for a data set with 39 values. We're going to let the software do it. We'll see in chapter 4 how easy it is to have R make this plot. But basically what we're looking for in a QQ plot is if the histogram was normally shaped, there will be one dot for each data point, and they will be exactly on that 45-degree line. If it's perfectly bell-shaped, perfectly normal, the points will be exactly on that line. What would you say about this distribution?
It's close.
It's fairly close. If we were to look at this histogram, it would probably be fairly close to a normal distribution. If you have a skewed distribution, it will be like more of an S shape with your dots instead of a straight line. Sometimes if you have extreme values, it'll have a big arch in it. We're going to use these as diagnostics later on. Okay. So I know you guys most of you have started this homework and pretty much finished it, so I'll fly through this. I'm going to show you a new data set. This data set is called the cancer data set, and it's a SPSS data set. Now, we learned how to use the Haven read_SPSS command to read it in, but the Rio import command does the same thing. Tyson, that's his favorite. Haven's my favorite. There's always more than one way to do this, but I'm just reading in this cancer data set, and I'm cleaning it up. So in this cancer data set, I'm going to rename all the variables to lowercase, so I don't have to deal with the capitalization. There's an ID variable for each participant in this data set, and then there's a variable called TRT. That's for treatment. They're either in a placebo or allo juice group. So this is a data set. I think it's real, but I can't guarantee it's not made up data. I think it's real. It's from an experiment with cancer patients who had oral cancers, I think of the throat mostly, and the treatment for that cancer often causes canker sores in the mouth because it attacks the most quickly dividing tissue, which is often the lining of your mouth, so it causes sores. So this experiment was to see if gargling and swishing with aloe juice helped clear up that condition and protect the lining of the mouth. So the subjects in this study were assigned randomly to either have the real aloe juice or a placebo, and they didn't know which one they had. And then we have what stage of cancer they're in. Stage 1, 2, 3, 4. And I think that's at the beginning of the experiment. So this is table F. Have we seen table F? Yeah. Now you can use table F with a continuous variable. And if you use a continuous variable like age, you can say n equals, now here I said n equals 8, and it showed us the top 4 and the bottom 4 for combined 8 most extreme ages, and it's done ... in the middle, because there would be almost a line for every person because it's a continuous variable. And we've done frequency tables for categorical variable, right? We've done these? Table F. F is for frequency.
Yeah, we did like.
Okay.
Good.
Oh, I was like, okay. Psych describe. I know most of you have been doing this in the homework. Describe is a really handy command that comes in the psych package. It has a lot of cool commands in it, functions. This will give you all the summary information for any variables you select out first. You have to select more than one variable or else it doesn't work. I don't know why. It's driving me bonkers. But for all the variables you list in here, separated with commas, for all of those variables, it will tell you how many values you have. Now notice, what does this 23 tell us? All these are 25, and this is a column labeled N.
There's
2 people are missing. Now, this is their age, this is their weight at incoming, and then this is the total condition, oral condition at intake, and then it's the total oral condition at weeks 2, 4, and 6. So this is like followed up every other week. And so two of the people didn't have the measurement at the last time point. Hopefully they're okay. So what does it give us? By default, just saying describe the data, by default it gives us the mean, the standard deviation, the median. This is trimmed. This takes the mean and it throws out the top and bottom total 5%. That's trimming. We don't use this a lot, trim. MAD is, what do we say? Median.
Absolute
Deviation. It's another measure of spread, which we don't use very often. Min, max, range. So you give us min and max and range. How do we find range? Subtract the min and max. It gives us skewness, kurtosis. However, we're only concerned if it's beyond 2 for normality. And this standard error is the standard error for the mean, which we haven't gotten to yet. It's not the standard error for kurtosis, and it's not the standard error for skewness. It's the standard error for the mean. They didn't label it very well. Okay, table 1 is another one of Tyson's creations in the furniture package. And this is called table 1 because in almost every journal article we write, the very first table describes the sample. So here we have, what's the size of our sample? 25. We end up with 14 placebo, 11 allo group, and there's the average, age, and weight. If it's a categorical variable, it'll list the count and the percentage for each available option for that categorical variable. If it's a continuous variable, it gives us the mean and standard deviation. Now, to do that, I just did the data set, furniture table 1, and then in the parentheses say which variables I want here. Pretty nice. Yeah, don't want to do that by hand. This one is a group-wise table. The only addition here is we put the dply or group by command, and then you put a variable you want the columns by. So I wanted a separate column for treatment, allo, and placebo, and it will separate that all out for you. Very, very handy. This saves a ton of time. We couldn't find a good package that did what we wanted, so made our own. Okay, box plots. So last week and the week before, I threw a ton of stuff at you. Who felt like they're in the deep end of the pool, like doggy paddling, trying to keep your head above water? Now things come slower. Always, we start with the data set, pipe it in, we're going to make a plot, so we do ggplot aesthetics. This time to do a box plot, you need an x and a y variable, both. And if you don't say x and y, the first variable will be the x variable and the second variable will be the y. I always try to label them x and y. Now, we're only doing one group, so we're not splitting it up, so we're going to just say x equals some text. And whatever text you put here will be the text at the bottom. And then age is going to be on the y-axis, and it makes us one plot, which we almost never make one box plot because it doesn't really tell us a lot. Box plots are more helpful for comparisons. So one way to do that is to fill the boxes in by a color variable. So you do that by adding in the aesthetics, x equals and y equals, but we say fill equals a variable. And if that needs to be, the fill variable has to be categorical, and however many levels it has, that's how many colors it will do, and it makes a legend for you. There are ways to make this look better, but that's just default. That's all we're going to worry about in this class. If you want to get fancy, come see me. I like fancy. Another way is to split the x-axis. So instead of doing fill equals, we can say x equals the name of a variable, and then it splits the x-axis by that variable. Now there's another way we learned how to do splitting plots. That was by panels. Facet, yep, so we can facet. So I've left x equals the text, and then I faceted. If I do the variable after the tilde wave, it puts them side by side. How do I make them on top of each other? Do it before the tilde wave, wouldn't make sense here. Yeah. Question?
No.
Okay. All right, so you can combine all the steps we've learned. So you can do a select and a filter before a plot. Usually a filter is a good one to use with a plot. So on your homework, you have to filter. You can write a statement using the greater than or the less than signs if it's a numeric variable. This is why we kept the gender variable around when we made the gender f variable and the major variable around when we did the major f variable. So who got to the compound requirement on the homework? You can use the and sign to require two things. I want to require that they weigh more than 150 pounds and are in the placebo group. Now, this is a little tricky. This threw me off for like the first year. I always type it wrong every time, and I saw that warning message so many times. I want them to be in the placebo group. Placebo is text, so it has to be quoted. 150 is a number, no quotes. So if it's a numeric continuous value, the DBL, double floating point decimal number, no quotes. If it's text, character, or a factor, you have to quote the text. Less than, greater than, this combination means greater than or equal to, you just put them side by side. The equal comes second always. But if you want it to be, a variable to be equal to text, you have to put a double equal sign. That's what I always got wrong for like a year. It took a year to train myself to type two equal signs. I did it wrong more than half the time. Because what that's doing is it's not making something equal, it's testing if it's equal. So it's going to filter and keep people where the treatment is equal to placebo. So it is equal to, that's why there's two equal signs. Questions? A little trickier. Okay, and then there was one of these on the homework too. What if we want it to be an or?
So
Yeah.
double equal.
Double equal.
We can use just one equal.
You cannot use one equal. It'll give you an error message. Because one equal is when you're going to make, say, x equals 5. You're going to make x be the number 5. But if you want to test if it's true or not, if x is equal to 5, it's the is equal to test equivalence, you need double equal sign. If you're going to set something equal to it, that's a one equal. And again, it took me a long time to get used to that. So be prepared. If you see a message and you're doing a filter command, ask yourself, and the error message is getting better. Every time they release a new RStudio, it gets better. I think it asks you, are you sure you didn't want two equal signs? So it's kind of helpful. Okay, so what if we wanted two options? Like the one in the homework says if they are either major, their major is either biology or psychology. Was it biology? Is that right?
Yeah.
There were two of
So
them.
by a factor and for a subset, is it?
Yeah, so you have a combination, but one of those variables could be more than one thing. So this is how you can do it. This is another special set of symbols. The percent, IN percent, says is the thing that, so here we'd say, is their cancer stage contained in this listing? So are they in stage 2 or stage 3 or stage 4? There are multiple options you want to include. So in this data set, there are also stage 1 and stage 5 and stage 0.5, I think. There's some other values. That's not the whole list. But if you want some of the values, not just one, you can list them and use that percent, IN percent. It comes in handy a lot. Okay. Now, on this one, this code does not look like the code that used to be here, and it does not look like the code that's in your homework. This is the place pivoting or rearranging data set from wide to long and long to wide form. The way the code does it, they've improved it vastly in the last year. I think it's about 6 months ago, they released some new code. So this doesn't look exactly the same as yours, so don't worry about it, okay? Just follow along the homework. The homework matches the encyclopedia. I have not updated the encyclopedia yet, but I updated the slides. If you have a repeated measure where you have week 2, week 4, and week 6 that are side by side, so you have a repeated measurement, we're going to have these later on. You want to make separate box plots for the week 2, week 4, and week 6 that are separate side by side variables. You have to stack. And the old command was gather. You have to gather those columns together. The new one is called pivot longer. And I'm not going to really focus on it until we get to the repeated measure stuff, like in a month and a half. But that's how you would do a repeated measures variable. You have to stack it together, and then you can make the side-by-sides. So don't worry about the slide too much. Look at the encyclopedia, hang out after class. So you can combine these plots. You can combine all of these steps. So we've done like one thing at a time. So here I'm doing repeated measurements, but I want to do it by stage, and I'm doing it for stage 2 and 4, ignoring stages 1, 3, and 5. So I can do a filter, and I can do a filter requirement. I can gather it or pivot it longer, and I can fill it and panel it. I can do all of those things together. Often we have to combine these different steps to get a plot to look at our data the way we want to look at it. It's often a really good idea to kind of, and the more you do this, the more you get in the kind of get the hang of it. But kind of imagine if I could make any plot of my data, what would be the best way to separate it out? And if you can kind of imagine that, then you can work through the steps that you would need to get there. On the homework, I'm always going to give you like some hand-holding structure. Do this, and then add one step. The book tries to, one step at a time. If you look at this plot for a little while, what can you say about their oral condition over time? Placebo versus allo, treatment versus control, and stage 2 versus stage 4. Is there a difference? Does it matter? Is the pattern different?
Yeah.
So the pink are the early stage 2. What's happening in the placebo in stage 2? Not much. The spread's coming down, but the averages or the center is remaining the same. What about with the aloe juice?
I don't know if it's worse or better.
I think this is like number of painters.
Getting worse.
They're getting worse. Again, I don't know if this is real data. So, what about stage 4?
More effective.
Maybe better here, but worse here. So the effectiveness of the treatment depends on whether you're early stage or late stage. It's called an interaction. We'll get to that later on in a month.
I just wonder.
Yeah.
What does number of condition mean when it goes high?
Oh, this is the
Yeah.
oral condition. This is like how many cankers how many sores they have in their mouth.
Oh, okay.
So like someone right here would have 15 sores.
Okay.
I think it was sores or severity. I don't remember. Yeah. I'm more concerned with the numbers more than how they measure them. But as clinicians, you guys probably have some of the other, like you're more concerned with what it means. I'm more like, what's the pattern? That's why it's good to work together. Okay. Can we start the normal distribution? We're not going to go over, but we have 25 minutes. We should be able to get some done. Are you sure? Any questions on chapter 3 before we move on? I don't want to leave anyone in the dust. It's not okay. Oh. Okay, chapter 4. I know you've all read the chapter. So, exploring quantitative data. Before you ever get to modeling statistical analysis, you always plot your data. Make a graph. Calculate or look at the overall shape and pattern with center and spread. Also look for outliers. Plots can help with that. Calculate the summary statistics, the center and spread, mean and standard deviations. Those are all prerequisites for everything else, always. And then we've gone through all that. Number 4 here is that sometimes a pattern in a distribution or a set of data follow a very clear pattern or trend that's so obvious and striking we can describe it with a smooth curve. That smooth curve is called a density curve. And the laws about density curves is they have to always be above the horizontal axis, and the area under the curve has to always be exactly 1. And area tells us about probability. Probability is represented by area. More area, more probable. So here are 3 different distributions with 3 different density curves. So we'll go across. So height. How would you describe the height of this population? I don't know who this is. Unimodal?
Yes, normal.
Normalish? Symmetrical? Centered around 66? What about that centered picture? Is that a normal distribution? Is that bad? Is it bad that our GPA is skewed?
No.
Not that way. Yeah, it's skewed that way. Okay. I think that a lot of times students in statistics class come out with this idea that normal is good.
Yeah.
Normal is what you want. That's not the case. Normal is common for some things, not for others. Does it make sense that this has to be normally distributed, our GPA, between 2, 3, and 4? Would we want it to be normally distributed? No. So we'd say this is skewed, positive or negative? Negative. Unimodal or bimodal? Ooh. There's one big mode and a smaller kind of, almost looks like there's another peak right here, right?
Yeah.
So definitely a smaller mode. This is why we say describe with words, not just give a number. So, it's got a fairly large hump, maybe 1 normal distribution of the mass between GPAs of 3 and 4, and maybe a smaller subgroup that has a GPA between 2 and 3. So it's kind of bimodal, but this is by far the bigger chunk. Yeah, you need words to tell this story.
Is that what you're looking for in like question 10 of the homework when it says describe completely?
Describe completely. If you're looking at a picture, yes.
Well, it says so it's the assume a normal distribution and gives you the mean and the standard deviation. And then it says describe completely the sampling distribution.
The sampling distribution, that has to do with the central limit theorem. don't know if we'll get that here. I don't want to jump ahead.
Okay.
But that's slightly different.
Okay,
But
because I couldn't figure out what.
you're going to have to say something about shape, center, and spread to completely describe it. Shape, center, and spread. Okay. Okay, what about this last distribution of tattoos? This might be tattoos here of Utah State students. Is it normally distributed?
No.
No. Is that wrong and bad?
No.
No, it's just a fact. What's the mode?
0.
0 by far. This kind of distribution we often call a J distribution because it's not just skewed, it's like way. I don't even, it's like there is a preponderance and oversaturation of zeros and then little bits trickling up. For this tattoos, is the mean a good measure of center? Or is median better? Or is mode better?
Mode.
Mode actually is here because the mode is probably what? Like 97% of the population is 0, or the sample. I don't know if this is the whole population or sample. Didn't say. The mode might actually be a good call for descriptive purposes for this distribution. So I would almost go with mode here. What center should we use here? They're very similar. Yeah. What about this one? Doesn't matter. They're nearly identical because it is so symmetrical. Yeah. Okay. Yeah. Okay. So this is the reason why we focus on the normal distribution. There's a lot of statistical procedures that we are going to focus on here. Correlation, regression, t-test, ANOVA. Focus on this shape of pattern of data. It's sometimes called the Gaussian curve because it was developed and published on by a guy named Carl Gauss. So it's the Gaussian distribution, the normal curve, the bell curve. So general rule, it is a bell curve. Part of the definition is a calculus formula that we are not going to focus on, but it's that if you go from the center out 1 standard deviation in each direction, under that curve will be the magic number 68%. These are 3 numbers you might want to memorize. From the center out, 1 standard deviation either side captures in the center a total of 68%. If we go out 2 standard deviations each way, it captures 95%. And if we go out 3 standard deviation, it captures nearly all, 99.7. How far do we have to go out to get all 100%? Infinity, both directions, to infinity and beyond. Okay, there's a good formula. You get to do calculus on it. If you're taking some other stats courses, we will avoid that. So the best way to determine if your data sample has a normal distribution is to plot it. Histogram's really good. And the other option is a QQ plot. This is a QQ plot for this same data that's in the histogram. Are they is that data normally distributed? Pretty close. Pretty close. Okay. Z-scores. Z-scores are magic, right? No, they're not. But they are kind of a cool thing, and they're a thing we're going to use a lot. It's called standardizing. We're standardizing because we're going from any units possible and changing the units to the same units, no matter what. The units are number of, not inches, not feet, not pounds, number of standard deviation. A z-score tells you how many standard deviations above or below the average a particular value is. So the formula is, there's 2 versions of the formula. What's the difference? The first one, population. Mu and sigma are the mean and standard deviation if we have the whole population of data. X bar and S are for the sample. Now, in the formulas, we're going to use X bar and S, but when we're writing our sentences and making our tables in APA format, what are we going to use instead? For X bar is going to be capital M, and standard deviation is going to be SD squished together, and both of those should be a italicized? No. Okay. Now this is a key point here in red. It's always, I have faculty that come to me still and have this not understood. Standardizing changes the units. It does not change the shape. It shifts everything up and down, and it compresses or stretches out, but it does not change the shape. If it was skewed before, and you make a z-scores, it's still skewed. Okay.
Is it the R score that changes the shape?
R score. R usually represents the Pearson correlation coefficient. And that's kind of, we'll get to there, I think in chapter 6 or 7. But it's the combination of standardizing two scores and summing the products. Yeah. Okay, so here is a problem. So this is time for pencil paperwork. These are the type of problems that are on the homework. These are the type of problems that will be on the quizzy test exam, whatever we're calling it, the assessment. Okay, 95, did anyone have a flag come up in their brain? 95%, 2 standard deviations from the center. 95% of the students at a school are between 1.1 and 1 meters tall. What kind of students are these? Are they college students?
Elementary.
Elementary, probably. Yeah. Unless you're my poor daughter. She's short. Okay. So, it does say assume. Yes, I know. Assume. Assume we have a normal distribution. Calculate the mean and the standard deviation. Anyone have any idea what we could do?
So your 2 standard deviations are going to be the 1.1 and 1.7. So along the lines down there,
Lines down here.
you go the last,
So the average is always in the center, and if we go 2 standard deviations this way and 2 standard deviations this way, in the center will be 95%, and that's between 1.1 and 1.9. You know how long I've been doing problems like this? 25 years. I still draw and shade a bell curve on all of these problems. Still. Because the first time I don't, my dyslexia kicks in and I get it wrong. It's kind of embarrassing when you're the teacher. Okay. So, I highly suggest you guys draw out the pictures too. So, how can we find the center and how can we find the spread? How can we find the mean? What? How did you get 1.7?
I mean the between.
Oh, 1.7 instead of 1.9. Okay. See, it's embarrassing when the teacher gets it wrong. There.
It's just going to be halfway between since it's normally distributed.
Since it's normally distributed, we know that it's symmetrical, so the center will be halfway between the two. So we can find that by, what math would we have to do? Average them. You find the center by averaging them. 1.1 and 1.7. Add them and divide by 2. 1.4. Woo-woo! Okay, there's more than one way to do the standard deviation. Anyone have one way that it could be done?
Taking the difference between the 1.7 and 1.4.
1.7 and 1.4, how many standard deviations will that be? 2 standard deviations. So you could subtract those numbers and divide by 2. What's another way we could do it?
The bottom and the top and divide by 4.
If you subtracted the 1.7 and the 1.1, we'd need to divide by 4. Both of those should give you the same answer. So that would be 1.7 minus 1.4 divided by 2. Here's a trick question. Well, not a trick question, a tricky question. If my standard deviation is 0.15, do I have to write the 0 in front of the decimal? Yes or no?
Yes.
Why yes? That's the first line I heard.
I think it was.
Because it's not a p-value.
It's not a p-value.
It's the-
Yeah. Could it be 1 point something?
Yes.
Potentially. So because it could have come out, there's nothing that restricts it to mandatory make it less than 1. We have to put the 0 in front of the decimal. Okay. Good job. Ding, ding, ding. Did we get the same answers? Yeah. Okay. So you have a friend who's in this population, and they're 1.85 meters tall. Woo! Now in green, I've written the mean and standard deviation from the last slide, so don't forget them. How far is 1.5 from the mean? .45. How do we get .45? Subtract the mean. Ugh. Oh, I have to do this thing again. The mean in the middle is 1.4, and they're over here at 1.85. So this original scale, what are the units on the 1.4 and the 1.5? What are the units? That's meters. So if we subtract them, it's the wrong picture, I'm sorry. If we subtract those, we get 0.45. So that's how many meters he is from the mean. How many standard deviations from the mean is he? 3. That's a beautiful answer. The way that I always do these curves to ensure that I get it right, and don't let my dyslexia come over me, is I always write the units under the curve, and then I write a secondary axis, and I label this z-score in terms of standard deviations. What's the center of a z-score?
0.
0. I know that without any math. I know if I convert meters to z-score, that's number of standard deviations away from the center will always be 0. Now how do I find out the math that said 3 is the magic number? What math would I do? I want to know what z-score corresponds or matches with the number 1.85. Now, you might be able to do mental math, but what's the formula we'd use? It's our z-score formula. What goes first on the formula? Just plain x minus the mean. Now, were we told that it was a population? It says of all, it doesn't say, but it's saying of all students is kind of implied in the sentence. So this would be mu over sigma. So we know this value is 1.85. Mu, the mean, is 1.4. And the standard deviation sigma, yeah, you're right. It's exactly 3 standard deviations. Wait. Is there a wait? These were nice whole numbers. What's the chance that it's always going to be a nice whole number? Never! Never in real life. That's why we let the computer do it. Okay, so here's our standard normal curve. This is the one I do not want you to memorize. I will give you all or part whatever you need to do the test. Goes on for like 6 pages in your book. I think I have photocopies left over from last semester too. But you're not here when you take the test. I'll get it included somehow. I'm going to work on that tonight. Tonight I'm going to get the test ready to go. All right, so who remembers using this standard normal curve in your last stats class, whenever that may have been? Kind of fuzzy in the back of your mind? Sometimes they're laid out a little differently. So let's look at this one. So this one it's like sets of 3 columns, and it like overlaps. So we have a z-score paired with it, the area from the mean over to the z-score, this little wedge here, and then a matching column that's from the z-score beyond. Now, what do we know about the shape of the normal curve? It is symmetrical, so it would be on the other side. So if you put negative z-score, it would just flip it to the other side. So it gives it to the nearest 10. Now, you're going to do calculations. Are they always going to fall on z-scores and probabilities that are identical to those numbers? No. In the real world, do we use that table? No. We're just going to use it for a few weeks in this class to get kind of our feet under us. What do we do in the real world? Use R. And it has like a billion decimal places, and we don't have to worry about this. In the homework and the text, go with whatever's closest. If it's in between, we usually go more conservative, but I will not take off points because it was in between and you chose this one and somebody else chose that one. Okay? I don't want you to stress about that because that is not really important in the grand scheme of things. Okay, so let's look at a problem that would use this. So we're looking at the same school, the same population. So we're using the same mean, 1.4, and standard deviation, 0.15. We got 1, 2, 3, 4. Let's see how we can do. First one says, we need the z-score for a student who is 1.63 meters tall. How do we get a z-score? Take the x value, 1.63, subtract the mean, divide by the standard deviation. Anyone have a calculator handy? This is the kind of math that you'll want to be able to do on the test. Anyone get an answer? 1.53. That's what I got. 1.53. Very good. Second one. Oh, now we're going backwards. They give us the z-score. Oh, and it's a negative. That negative's kind of tiny there. A negative 2.65. There's a shortcut and there's use the formula. Do I care which one you do? No, I don't. So let's see. What shortcut would you do? You said shortcut.
Well, I said the short kid.
Oh, short kid.
the shortcut would just be to drop the negative and then add it back on after you.
Yeah. I would always like draw a curve because, you know, I like to be right and I'm lazy with memorizing things. My dyslexia makes the memorization hard, so I always have to go back. And so I'm going to say meters is this one, z-score in terms of standard deviation underneath it. Average is 1.4 meters, which is the same thing as 0 z-scores. I always have to draw this. I can't not draw it and get the right answer. So they're at negative 2.65, and we need to know how many meters tall they are. So one way is to take our formula which is the, oh, I did it wrong. What did I do wrong? It's just x. We know mu and sigma. You can put those numbers in there. This time they gave us a z, so you could solve the formula for x. There's another way you can do it, though. You can start at the 1.4 and subtract. How many standard deviations are we going to go down? 2.65, and how big is a standard deviation? 0.15 meters. Either way will get you the right answer. So if I was to plug in what I knew, I'm going to come over here. That's my z-score. X is the thing I don't know now. This is about some of the hardest math we do in this class. The rest is just hard thinking. How do we get x alone? What do we get rid of first? The 0.15 or the 1.4? 0.15. How is 0.15 connected to the x? It's
dividing.
Fraction is divide, so you do the opposite to get rid of it. It's times. Whatever you do to one side, you do the other side. Oh, college algebra. Okay, calculator says 0.15 multiply negative 2.65. What?
Minus
0.4?
almost.
Anyone have a calculator? I didn't write this part down. 3975. You were right. Good mental math.
Now I have calculator which says
You rounded off. Yeah. Now, careful with your decimals. No one wants to miss a point on the test because of a decimal going missing. All right. And then how do we get x alone? Add 1.4. Oh, this is about negative 0.4, and this is 1.4. 1.
1.0025 above.
So how tall is this kiddo?
1.0.
Short. Yes, short. Okay. All right. What is percentile rank? This is the last one we'll do, and then I'll do the rest on a recording for you.
you take the area and
Area. Let's see. Erase all. Draw my trusty curve. Well, I've got a height. So the original axis is in meters. And now I'm going to go to z-scores in terms of standard deviations. Okay, if I was going to shade percentile rank tells us the percent of students that score below. So this is where the curve really comes in handy. If I shade below, I keep going across the middle. All of that area is the percentile rank. But is that the kind of area that's in the table? What is the kind of area that's in the table? It either says from the center over or
Value.
from the value and beyond. This is the beyond. The beyond is always in the tail, like a little teeny tail out there. So what do I need to do? I can look up the beyond area in my table, but not based on meters. The table requires that I convert to a z-score. So this is like a multi-step problem. We're like moving up from freshman year to sophomore year, junior year, senior year, grad school. Okay, so we got to convert to z-score. How do we get a z-score? What buttons am I going to push my calculator? 1.51 minus 1.40 divided by the z-score is 0.8733. Is that what you got? No.
Yeah, 0.73.
That's what I got.
Point 11 divided by 0.15.
As 0.7333.
7.3. Okay, I must have wrote it wrong. Okay, so then we need to go to our table. Okay, so which 1.73? That's a z-score. And if you go to the bottom, you haven't found it, go to the next column, haven't found it, keep going. Oh, it's not showing on this table because I skipped the page. In our Canvas class, in the files, I'll link this on the homepage. In the files, I have a copy of all these tables. And it is our cheat sheet. Ooh, that sounds good. It's not here. You would look it up, and that area would be to the, we're out of time, would be to the, when you look it up and take the table, I put 0.87. I must have done something wrong. Oh,
That was 1 point.
it says 1.51 here, and I did 1.53. That's why. I don't know who's right. I don't know if the error is when I typed the slide or when I did the calculation. Somewhere I didn't have time. The table, the beyond area, tells you out here. So you can use what's the total area under there? 1. So if there's 19% here, or 0.19, then you subtract it from 1 to get the area on the other side. So you can use the fact that it's symmetrical and the total area under the whole thing is 1. What's the total area on any one side? Half or 0.5. I highly, highly suggest you get used to drawing these curves because it gets a little confusing if you don't. Okay. Good? I'm going to go ahead and stop the recording.